speaker for the day, we now request Mr. P. Senthil Kumar, Honorary Secretary, IIF Chennai Chapter, to introduce Mr. Senthil, SP, General Manager R&D, Sundaram Clayton Limited, to our audience.
Vanakkam. Can I have more louder, please? Good morning. Lunch is long way. Okay. You have to bear with us for another 1 hour, 15 minutes. Okay. Little be cheerful. Okay. I'm pleased to introduce the speaker. I think our committee has chosen just because I'm sharing the same name. Thank you very much. Mr. S.P. Senthil is currently working as a General Manager R&D in Sundaram Clayton Limited Die Casting Division. And he has done his Bachelor Engineering in Mechanical in Mogamika Engineering College and M.Tech Automatic Technology in IIT Madras. And he is working in SEL from 1999, almost 25 years. Very long years, sir. Position in production, quality, design and engineering. Currently responsible for process quality and assurance function. And speaker has given very little is biodata to read out. I'm sure that his presentation will talk tons about it. Thank you very much, sir. The floor is yours.
Good afternoon. Okay, this is just a case study of what is the techniques that we use for improving quality. So I'll just briefly go through this case study. This case study is based on robust optimization. It is a design of experiments technique. So we use this technique to improve quality in our products that we produce. So just a brief introduction of ACL. I think most of us know. So we are a $250 million US dollar truck focused company, and we provide wide range of solutions in aluminum die casting, starting from high pressure die casting, gravity die casting, low pressure die casting. And our sustainability goal is to achieve carbon neutral by 2040. These are some of the parts that we make for commercial vehicles, passenger cars, two-wheelers and other things. And we have plants across India and one plant in US. So before we start with this robust optimization Taguchi technique, I'll just give a brief of how this technique is developed. Professor Dr. Genichi Taguchi, he developed this technique. It is an experimental, structured experimental approach where we use different parameters, how to identify parameters that affects the quality of a product. So it is a controlled experimental technique where we can use different parameters that we use in general casting processes and which parameters affects the quality of the product. The main aim of this technique is to avoid variation or to make the process more robust so that it takes care of the variation. And the overall objective is to produce high quality product at low cost. And the experimental design proposed by Taguchi, it is an orthogonal array technique. So one benefit of this orthogonal array technique is that we don't want to do like a full factorial experiment where we need to do more number of experiments, whereas in orthogonal array the number of experiments is reduced, so we can quickly conduct the experiments and obtain the results. His philosophy is like generally quality should be designed into the product and not inspected into it. So he mainly asks all the people who are following his techniques not to use this technique for firefighting. So in the initial design stage or in the product development stage itself, we have to use this robust optimization technique so that we develop products which, when it is introduced into mass production, produces the right quality of part. And he always says that whatever the deviation that we are getting from the target, how to reduce the variation. So variation is the main key factor which causes all failures in the process. So how to reduce variation, that is one thing which is very important. And the cost of quality should be measured as a function of deviation from the standard, not only from the producer, also from the where it is used. So till the end life cycle, the cost of quality has to be measured. So I'll just give a brief of which part that we used. So it is a front housing part, and it has two variants in casting, and after machining we have two more variants. And it is an ALS9 Cu3 alloy, and the part weight is 17.3 kg, so it's a very big part. And we produce it in a 3,200 ton die casting machine. And initially when we started this project, we had very high leak rejection. The leak rejection is also high, and moreover it is varying. It is inconsistent across months. So it is a significant problem, because of which we get some customer complaints also. And because of customer complaints, sometimes we need to do some additional rework and other things. And our scorecard with customer is also getting reduced. And being a heavyweight part, because of this rejection, the overall rejection of the plant is also increasing, and we also have capacity loss in machining as well as in casting. So we took a target to reduce this rejection or to eliminate this rejection using a technique called squeeze. So which one of our previous speakers also told, it is one of the technique to reduce shrinkage porosity in die casting. So we take the first Pareto part, that is the leak. Even though the leak is detected after machining and leak testing, and sometimes even at customer end, but the occurrence of the leak is mainly because of the casting process. The defect is generated in the casting process, whereas it is detected at the subsequent stage after a lot of value addition. So if you see for this particular part, the leak is occurring. How to identify the leak occurring location? We use a bubble test, soap bubble test, to identify from where it is leaking. So once we understand from where it is leaking, then we can identify the cause. When we check the part in X-ray, for example, from where it is leaking, if you try to identify the defective samples in X-ray, we couldn't find any significant defect in X-ray, but still the part failed in the leak testing. So next step, when we move these parts to a next step of X-ray, that is the CT scan, computer tomography, where we can easily identify what is the leak connection path. To solve any leak problems, we should know the connection, from where to where it is getting connected. So that is the first step to identify and solve a leak problem. So we did a CT scan from which we can identify how the leak is getting connected from this hole to this hole. So this is that leak path which is creating the leak after machining and leak testing. So this is the summary of observation. The leak is detected at in-house as well as at customer end, and the leak is testing done at our end at 4 bar, whereas at customer end it is done at higher pressure because of the assembly, and shrinkage is a defect that creates a leak. So this is a brief explanation of what is shrinkage. Shrinkage is nothing but a void when the aluminum metals changes from liquid state to solid state. This is created, and this generally appears in the thick section of the part. So like what we also understand from the morning, squeeze is one of the technique to eliminate shrinkage porosity. It is nothing but adding of feeding of metal, not like adding, it is feeding of metal. When the aluminum metal solidifies, it because of the density difference between liquid to solid, it creates voids, which is inevitable. But when you use squeeze, we can feed this shrinkage porosity, and then we can make the part defect free. This is an example of with squeeze and without squeeze how the defects are getting eliminated because of the additional metal that is fed by the squeezing operation. And there's a robust optimization. We have a structured 8-step approach. It starts with defining the scope of optimization. So where we want to work. So what is the scope? What is the area that we want to take? And then we need to identify the ideal function and the response. Next is develop signal to noise strategy, and then select control factors and levels. This is an orthogonal array experimentation. Then we execute experiments and collect data, and then conduct and interpret data analysis, where we use signal to noise ratios. I will explain in the subsequent slides. Then we need to do optimization, predict, and then do a confirmation trial. And finally, from this experimentation, generally all experimentation, we need to have some lessons learned. So from which are all the factors that is influencing the response. So we will get some learnings and how to use these learnings in the future projects. So one by one I'll briefly explain the different steps. So this is a first level cause and effect diagrams to identify, to take what all the control factors that we want to take. So we make a first level cause and effect diagram for the shrinkage porosity, and then this is the level 2 cause and effect diagram, which I don't want to go in detail, but I'll explain. Okay. This is the first step. So you need to define what is your scope. So what are the areas that you want to work. So here we have taken the scopes as squeeze system, part configuration, and the die configuration. And the out of scope items are like the die casting machine injection parameters, and then the spray system, cooling system, and metal composition. So these are out of scopes, and from the in scopes we'll select control factors. So based on the in scope, the control factors are selected. And this is called a P diagram. So to briefly explain, these are the these are the control factors. There are around 8 control factors selected for experimentation, and the system in scope is a squeeze system. Generally, there are different types of experimentation available. One is called dynamic response. This is called smaller the better. Then it is called nominal the best, higher the better. So different types of experimentation is possible. Here we are, because it is a porosity volume, so smaller the better is the response for us case. And the noise factors, variation in metal temperature and variation in die temperature. One main advantage of this Taguchi method's robust optimization is there are noise factors available in all processes. Yeah. And especially in die casting, there are a lot of noise factors. These noise factors are factors that we consider as which we cannot control, or it takes a lot of effort and cost to control. So our aim is to make the process robust. So even though if there are some noise factors available in the environment, the process is so capable enough to produce good quality product even with these noise factors available in the factory environment. So his main aim is to make the process more robust against these noise factors. So the noise factors plays an important role in this experimentation, and the noises are compounded based on their effect on the response. Higher, one is called high and one is called low. This is called compounded noise technique. And these experiments, to avoid a lot of effort in implementing these experiments in the shop floor, we decided to do all this experimentation in simulation. So we use magma simulation to do all these experiments to identify which is the best combination, and from the best combination alone will be tried in the shop floor. So these are those control factors and different levels. One is the current level, and one level below and one level above is taken for experimentation. And some factors are 2 levels and some factors are 3 level, which we can see. And this is the L18 orthogonal array layout, where for each experiment what is the factor and what is the level that we need to try. So there will be totally 18 experiments for one noise condition and another 18 experiments for another noise condition. So total 36 experiments in total. And these are the actual experimental layout with the selected factors and their levels. And we calculate the response. The response is the porosity volume. So from each experiment in simulation, we calculate what is the porosity volume, and then we tabulate all the porosity volumes. And being porosity, the smaller is the better is the response. So where we get smaller values, it means those experiments are giving better results. And this is the response graph. So smaller porosity volumes are observed in some experiments in both high noise as well as low noise condition. And this is called signal to noise ratio. So higher the signal to noise ratio is better. What do you mean by signal to noise? Signal is the desired effect, noise is the undesired effect. So he wants to always try to increase or optimize the desired effect and reduce the undesired effect. So the numerator will be the desired effect and the denominator will be the undesired effect. So this is called signal to noise ratio. So higher the signal to noise ratio is better, and mean is what smaller is better, because the mean is porosity, so smaller is better. So based on this, the optimum condition is identified, and this optimum condition is also again simulated in simulation to predict what is the expected response out of this, and then we also do a confirmation trial in the shop floor. So this optimum condition is decided, and then it is taken to shop floor to do the experimentation. Generally, if you use a squeeze, squeeze is nothing like a cylinder which is operating with a pin. So to identify what is the correct stroke and what is the correct delay time, those are the 2 important parameters that we need to identify. So this is done like that. So based on the experimentation values, we tried in different delay times, and we found there are good responses reached when we have a squeeze delay time of 4 seconds. And the same is also confirmed in X-ray. When we do different trials and then check the paths in X-ray, we found at a squeeze delay time of 4 seconds, there is no porosity in that location. And this is what also we got from the magma simulation experiments. And then the leak rejection on that particular location got eliminated. But then the overall leak rejection is still there, and this is because of there is also leak from another location, for which, so one location is solved by this design of experiments using Taguchi method, whereas still there is another connectivity passage between these 2 holes, this machined hole and this machined bore. So for which we improved internal cooling in the die, and then this location also the leak rejection is getting eliminated, for which we provided jet cooling. This is also another technique to move the porosity. This is not to eliminate, whereas in squeeze we can eliminate the porosity. In jet cooling we can just move the defect away from the machining. So these are the images of die temperatures, and then radiography images showing that the defect is moved, and then the leak rejection has come down to 0.8. So one method is doing the experiment. Then the other important technique or understanding that we need to have is what is the lessons learned. So from these Taguchi methods, there is an way to identify which factors are influencing the effect. So if you want to see which factors, then based on that, it will give some technical learning. So one important parameter is the effectiveness of squeeze is better when we have more delay time. And after a particular delay time, the effect will, the pin will not move. So to identify what is the best delay time. So that is possible by this experimentation. And then instead of squeeze, there is also one more way of, if we have some product modification to reduce the thick mass, that is a much better way instead of squeeze. So we need to try to approach customer to get a weight reduction. If that is not acceptable to customer, then we can implement a squeeze and try to reduce the shrinkage porosity. So like this, we had developed some learnings, and we are implementing this in other projects that we have squeeze already running. And one of the key learning from the robust optimization is all processes are energy transformation. There is an input energy, and this input energy is getting transformed into the required output. In this energy transformation, there will be a lot of losses. These losses only create defects. So if you see the P diagram, it focuses on the energy transformation. What is the input energy and what is the output energy, and what are the noise factors that influences this energy transformation. So robust engineering is basically adopted to discover this technical knowledge, and generally defects occur due to loss in energy transfer. If there is excess energy transfer or less energy transfer, the defects started occurring in the process. So robustness is to make the system more robust against or insensitive to noise. So these are some of the learnings that we have from this project. And one thing is, like, instead of doing all these experiments in the shop floor, if you are able to do a prototype or a simulation, then the effort required to implement all these experiments, because it is all 36 experiments, it takes a lot of efforts. So if we can do a simulation, shorter cycle time simulation, then we can quickly identify what is the optimum factors and levels. Thank you so much, and if there are any questions, I'm happy to take them. Thank you. If there are no questions.
Yeah. There are no further questions. We'd like to felicitate our speaker for the day. We now request Mr. K. Hema Prasad, Council Member, IIF Chennai Chapter, to felicitate our speaker, Mr. S.P. Senthil, with the Angavastram. To now felicitate our speaker with a memento, I now request our senior member, Mr. K. S. Anbuselvan, National Council Member, IIF, to felicitate with the memento.